Today is the 52nd day of Leetcode 75 challenge. Let's begin with the 52nd question. Question 2462. Total cost to hire K workers. The level of the problem is medium. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. So you are given a zero index integer array which is named as cost, where cost of I represents the cost of hiring the ith worker. Pretty simple. And you are also given two integers, K and candidates. K represents the number of workers you need to hire. Basically, K is the number of workers we need to complete our work. Basically, the number of workers you are going to hire. And candidates, the maximum number of available workers to consider from both start and the end of the array in each hiring process. So this basically represents the number of candidates which we can grab in one hand from the first half or the first starting of an array and the last end of the array. Okay, this is the same which will become by taking the candidates array. So let me explain you this scenario by taking an example of cost array as some values. I'm writing 0, 1, 2, 3, 4, whatever the values are here. Okay, and K is basically the workers we need. Okay, needed workers. Okay, and candidates. Candidates is basically the capacity of our hand, you could say capacity of our hand, that at once how many persons we can consider. Basically, you must conduct exactly k hiring sessions, hiring one person per session. Okay, since you have to hire k per people, right? So for hiring k people, you will do k sessions. If three people you have to hire, we will do three sessions, and in each session we will hire one person. Fine. And in each session, you will choose a worker from the first candidate workers or the last candidate workers. So if candidate is supposed to, okay, the value of candidate is 2. So or it says that from the beginning, you will either take two values and from the end, you will take two values. So you will grab basically two employees from the first and two employees from the last. Got it? It is what written here. That is the meaning of candidate, and K is the number of employees you are hiring. Fine. If candidate value is 3, then you will be hiring first three element. You will be considering first three employees and the last three employees. Okay, that's pretty clear now. Now from these available options, we choose the worker with the lowest cost. Okay. Now, if what it's trying to say that if multiple workers have the same lowest cost, choose the one with the smallest index in the original array. What it is basically trying to say is that, for example, you chose first two candidates, right? If candidates value is 2 and last two candidates, right? And out of these two, you will try to take the minimum uh, candidate with the minimum value. So in this, this is suppose 4 and this is 5, right? And this is 0 and 1. So minimum out of this 4, we have 0, right? So we will choose 0. And suppose if you had two zeros in this candidates array, basically, so you will be choosing the one which have the lowest index value. So here the 0 value is in 0 index, and this value is in 1, 2, 3, 1, fourth index, right? So you will choose the 0th index. So this is what it is written here. From these available options, we choose the worker with the lowest cost. If multiple workers have the same lowest cost, we choose the one with the smallest index in the original array, right? And after a worker is hired, they are removed from the pool and cannot be hired again. And if fewer than candidates workers remain on the either side, consider as many as possible from that side. Okay. And repeat this process until exactly k workers are hired. So for example, if suppose the candidate value is given to us is 6, fine, which means that from the given array I will choose 6 from the first and 6 from the last, right? But if the value or the size of the array itself is smaller than candidate, we try to choose the minimum one. Okay, and we try to complete the all k required numbers. Suppose if this is the case, I will be taking 0, 1, and 2 if k value is 3 to complete the particular case, right? It is what written here. If fewer than candidate workers remain on the either side, considered as many as possible from that side to basically complete the k workers. Okay, so the question is pretty straightforward. An array is given to you. K is the number of workers you need to hire, and candidate is basically the sub array from the beginning and from the end, from which you will try to choose the minimum uh, cost for the particular worker, and you have to complete it for the k workers. That's all, right? And at the end, you will return the task is to return the total cost incurred in hiring the k workers. So basically, the number of basically the summation of the employees or the workers you took from the cost array. You have to sum that up, right? And the constraints are the cost array length could be from 1 to 10 to the power 5. The cost value also could be from 1 to 10 to the power 5. And k and candidates value could be same, which could be from 1 to length of the cost array. Fine. I hope you understood the problem explanation. Now let's move to the next slide. Now let's understand the input output explanation. So here, if you could see, we are given a cost array, the number of workers required, and the candidates we will take in one go. So if candidate value is 4 here, the first 4 are here, correct? And the last 4 are from here, right? And the minimum from here is 2, and minimum from here it's 2, right? But since both of them are minimum and the value is same, we will try to take the one which has the lowest index value. So here in this case, this has the lowest index value, right? So 0, 1, 2, 3, right? Therefore, we take these two, okay? And this 2 we will remove it. Okay, now we have this. Now again we will go and we will try to take 4 candidates. These are the 4 candidates and these 4 candidates. Okay. Now here minimum is 7 and here it's 2. So obviously minimum out of these 2 is 2, right? I will take this one. So this also gets removed. Now the candidate value is 4 again. So we will take 4 again, right? So 1, 2, 3, 4. Great. And again from the back 1, 2, 3, 4. Fine. Now from this first half 7 is the minimum and from the second half 7 is the minimum, right? And the index for 7 is the same one, right? So we will take that. So what comes our output to be? 7 plus 2 gives me 9, 9 plus 2 gives me 11. So 11 is our output. So that is what is given here. So I hope you understood the explanation of the input output. So let's move to the next slide. Before going to the further slide, let's understand what is min max heap or min heap or max heap concept. Fine. So what is a heap? It is a spatial binary tree or a complete tree where the value of each node is either, in min heap case, smaller than or equal to its children, max heap greater than or equal to its children. So basically, it stands like this. This is a tree, and if you're looking for min heap, how it works? Okay, let's see here. Every parent node is less than or equal to its children. Suppose if this is -1, it will be 2, and this will be 3. It will be 5, it will be 6. Okay, it will be 10, it will be 20. So if you could see, so this is a parent node and this is smaller than any other node present here for in the children. Okay, now 2 is the parent node and 5 and 6 are its children, and these children are greater than the parent, which is 2 here. That is what is written here. Every parent node is less than or equal to its children. Okay, the root contains the minimum element used when you use to fast access the smallest element. So basically, every parent element will be smaller than the children element, and for the max heap, it will be opposite. Every parent element will be greater than its children element. So here you could see this is the parent element, right? For this, all the children is below it, and it is greater than the all the children present under it, right? If we take 10 as the parent element, 6 and 5 and 8 are smaller than 10. 10, right? Because 5 and 8 are smaller than 10. Similarly, if we take 11 as the parent node, 2 and 3 are smaller than it. So what is written here? Every parent in a max heap case node is greater than or equal to its children. So basically, if this is the maximum element, okay, all its children will be minimum to it. This is the maximum element. All the children below it will be minimum to this, fine. And this will be minimum to this particular node, but this will be maximum to the below children's, fine. This is how it goes. Now, why it's efficient, right? According to the time complexity, if you could see, insertion takes log n time, deletion of minimum maximum takes log n time, and picking of the element takes over 1 time. Now, here I've done reheapify. Reheapify is the concept of how the heapify thing works in a tree, right? How heapify works. So basically, it means that whenever you delete a node, we have to reorganize the complete tree, right? Or how to delete a node in the middle, or how to delete a node at the end, right? This is what a heapify does. So this is a different concept or different thing to learn about. I will create a different video for it, fine. A space complexity comes out to be O of n if we store the elements, otherwise 0, okay, or O of 1. Now, this is mostly efficient for solving the kth largest, smallest element problems, priority queues problems, median finding problems, and heap sort kind of problems, fine? Where mean max heap is used, okay? I've written some kind of questions here, or you could say examples of things where you could use this particular topic, okay? In priority queues, it is mostly used in C++, you could use this concept, okay? Like elements with high priority are served before the lower priority. Priority queue is basically mean heap only, okay, and max heap. But in uh, Python, if we focus on Python, there is nothing such as a priority queue directly, okay. So what we do, we use Heapq to solve our min max heap concept problems, fine, which is the concept of heapify also here, okay. We'll learn about this. Now, Dijkstra algorithm uses this mean heap concept. Top K problems uses this mean heap concepts when we have to find the largest or the smallest element efficiently. Heap sort uses the min max concept and it takes n log n time complexity. Okay. A median of a string use mean heap and max heap together to maintain the lower and upper halves of the data. So these are the questions, examples, or topics where you could use the mean max heap concept. Okay. So I hope you understood the concept of min max heap. Now let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. Okay, let's do that by understanding the goal first. So we are given an array cost. Okay, an array is given to us, and where cost of I is the cost of the higher of that ith worker, right? If there is two, so this means that this worker cost is two. Okay, now we need to hire exactly k workers in the k stations. Fine. In each station, we can choose the worker with the lowest cost from the first candidate workers or the last candidate workers. So please keep that in mind. Here we are trying to get the lowest candidate or the lowest cost candidate or the worker from the cost array, right? Every time. So keep that in mind. So therefore, we have to iterate or do something for that particular candidate subarray to get the minimum each time. Okay. So if you get in a hint here, what I'm trying to say, right? Every time we have to put out the minimum from both of the sides. If there is a tie, we try to pick the worker with the smallest index. That makes sense. Now, after hiring a worker, they cannot be hired again. So we have to basically pop it up. Keep that also in mind. We have to pop it up also, right? So I think you're getting the intuition where I'm going with it. And our goal is to minimize the total cost of the hiring K workers, right? This is a simple thing. We have to just take the sum of the worker cost which is popping and we have to sum it up. That's all. And after that, we have to remove that particular worker from the array also. Okay. So how we will do that? So let's visualize this process. Okay, so I've taken an example here with the candidate value is 2. Okay, I have not considered k value till now because that will make sense later part on the later part. Okay, let's figure this out how we're gonna do it. So, so what is our question is saying? If the candidate value is 2, we try to take the first two values and the last two values. Okay, now from this we try to take the minimum. So for this the minimum is 2 and for this the minimum is 1, right? So we'll after that we will take the minimum of these two, which is 1. Make sense? Now, each time if this is done, after doing this, we will pop this. Okay. And again we will do the same thing. So this will become the last two elements now, right? So we have popped 1. Okay. Now here 2 is the minimum and here also 2 is the minimum. And the lowest one is lowest index value 2 is this one, right? Because both the values are same. So we will take this one, right? We will and pop it. So if you could see, every time we're trying to get the minimum, okay? We're trying to get the minimum value and how to get a minimum value each time without iterating the sub array. I will call it as a sub array again and again. We could use a min heap, right? Because using a min heap always will restructure the particular subsequence and give me the minimum value at the top. And I don't have to iterate all again and again every time. Correct? So, okay, now we have figured out that okay, we can use a min heap to solve our problem. But how to do it, right? So what we will do, we will try to take 2 minutes. Let's try to take 2 minutes, right? And I will put the first two candidate values, which is 2 and 3 after restructuring, and here it's 1 and 2 after restructuring, right? And I will try to pop the topmost value or the minimum value which I will get from the min heap, and I will compare that which value is smaller, right? If this value is smaller, right? In this case, so what I will do, I will remove this array from the min heap, okay, or that value from the min heap, okay. Now, after doing that, it's practically impossible to remove and restructure the original array again and again, right? It will be a lot of work to do. So, what I can do, I can take 2 pointers in that case to solve our issue. Okay. So, what we can do is that we can put a left pointer, limit L pointer and R pointer, right? And R will go up to 2 points or 2 indexes because C value is 2. And it will come and stand here and it will put all this value into this particular uh, min heap. And similarly, with the left pointer, will also come till here and put all the values into the min heap while coming through the view. Okay. And after that, as I said you, we will pop the minimum value from the min heap. We will pop. We will basically take out minimum values from both of the min heap, compare them, and the one which is minimum will permanently pop it from the min heap. Okay. Another one which is compare just like here, the two was smaller than one, right? So we didn't pop two, we just popped one. And after that, what we'll do, and as you can see that this is left, this is right. We have popped the value from the right hand side, right? So what we will try to do, we will move the R from this end to this end, okay? And we'll push this value back into the main heap. Now, okay. Now what will happen? This will get restructured, okay? And this will become as 2 and 7. And after this becomes 2 and 7. And when we will try to pop the values, what we will get? We will get 2 and 2, right? Now, since the values of both the values from the both the mean heaps are same, we have to check for the index, right? For that, what we will do? We will take and see what's the value of L. It's 1, right? And what's the value of R? It's 1, 2, 3, 3, right? Now, since L is less than R, we will take that. And if we don't do that comparison also, it makes sense because even if we don't compare both the indexes, it will make sense to take always the left mean heap value because the pointer which is coming from the left will always have the index value smaller than the pointer coming from the right. That makes sense, right? That will always make sense. So that is why even if we don't compare left and right pointer indexes, we can just directly see if the both values are equal from both the mean heap. We can just return this particular one, or we can just pop the particular one, right? This way we can compare it. Now there could be a case we have seen before. What if L is also here? Just there is a case and R is also here. That is taken as considerable one case, okay? Because if you can remember in the example input output explanation, we had 2 plus 2 plus 7, right? And 7 was coming in both the left and right side of the subsequence of the candidate size, which was 4, correct? So here we have to keep that in mind that L and R could be equal. But as soon as they cross each other, that will not make any sense. Fine. So this will continue up to which time? If you remember, they have continuously said us that there would be k sessions, right? So basically, until and unless we get k values, we will do the iteration. As soon as we get the k values, we will stop the iteration there and there itself. But if the size of the array is less than the candidates, that will also get considered automatically because even if the size is less than the candidate, we will take all the k values which is minimum. Okay, we will try to take the minimum ones. For example, if candidate value was suppose c equals to 7, right? That's not possible because it will go out of bound. Correct. So what we can do, we will iterate from front and back both until and unless the L value is less than the candidate and also L is less than or equals to the R value. Okay. Till that time, we'll come from front and back, vice versa. Okay. This condition will be written in two ways. So that way, we will have both the all the values in our min heap 1 and min heap 2, or min heap left and min heap right, and we will pop the minimum from out of it. For example, how it will go is that since L is less than C, okay, in this take the scenario in this case, what we'll do, we'll push all the and L is also less than R, right? So what we'll do, we'll push all the values here, uh, whatever the values are, let's 3, 2, 7, 7, 1, and 2. Okay, I have not restructured it. Okay, so what will happen after getting restructure? We will get 1 first. Okay, if k value is suppose 3. Okay, then we will consider 2. Then again we will consider 2, right? Because now this way we will get all the values, right, and we will increment the session. Okay, so I hope you understood this visualization process. Uh, it will be much more clear to you when we go to the next slide. Now, how we can simulate this? Okay, what we'll do, we will try to initialize 2 pointers as we explained earlier, which will start from first and which will start from the end of the array. We will have 2 min heaps, left heap and right heap, to manage the first and the last candidate workers. That makes sense till now. Okay. Now, while highest is less than k, highest is basically the counter which will check that how many candidates we have hired till now, and it has to be less than k, because if k value is 4, based on 0 based indexing, it will go from 0 to 3. Okay, that is the basic thing to understand. Now we will fill the left heap. Now here it comes the tricky part. Now, as I explained here earlier, this particular case, right? Now what will happen? We will try to fill the left heap with values from the left up to the candidates or until pointer cross. Why pointer cross? Because suppose this is the array given to you and candidate value is within the range. Okay, suppose the candidate value ends here. So with the left pointer start and right pointer start from the back, we have to push all these values into the min heap or the left min heap, and this all values into the right min heap, right? That makes sense. So that is what is written here. We fill the left heap with values from the left up to candidates. Okay, take take this part up till here. Okay, and fill right heap with values up to from the right up to the candidates. Okay, make sense? Okay, and after this we will pop the values, right, or what will happen, this will increase, and again the same thing will happen. Now but what if happens that the candidate value which is given to you is greater than the given array? Okay, or what if after copying the values from the array shrinks to a certain size which is smaller than the candidate? Two things can happen. Now in that case, what you will do, you have to still complete all the k workers, hiring of k workers, right? So in that case, you can start from either back or front, right? It will do the same thing. But if you start from the left, this is what is written here, then what will happen? Fill left heap with values from left until pointer cross. Okay. This way, suppose if the array got shrinked this size, okay, and C was suppose 7 and this is size of 3. So you need all the workers in the heap, right? So what we will do, we will start from left and we will go up till right, putting all the values into the left heap, min heap, basically left min heap. And from there, we pick at the tops of both heaps to find the smaller cost. Okay. And this way we'll put all the values, and there might or there might not be values in this particular heap, right? What happens if there are no values in a particular heap, right? What will happen in that case? So since we will be popping this values from this left heap and right heap, and we will store it somewhere, right? Let it be left value and right value. So what we will do, we will have the infinity here. Okay, why infinity? I'm saying by chance, if this min heap, taking this case where the C value is greater than the size of the array, this gets filled up, but this remains empty. Okay, but if this remains empty and you pop some values from here, okay, you have to compare it with the right. Okay, so in that case, we have popped, suppose it was 0, right? You popped it and you stored it here. So 0 is smaller than the right because right has the max infinity. Okay, so that our code still continues in that scenario. For that scenario, we have to put both left and right as infinity initially each time when we pop. Okay, so that we can compare and take the minimum value out of it. I hope this makes sense. This is not a rocket science to understand this particular thing, why we're taking the infinity max infinity. Okay, now if left min is equal or right less than or equal to right min heap or left min or right min, we pop from the left heap because as I said, the value could be same. A value of the left min heap could be smaller than the right min heap, or it could be same to the right and left both. Right? In that case, if both the values are same, taking the one from the left min heap makes more sense because that value has been taken from the initial side of the array, and that value's index will always be smaller than the taken from the back. That was explained earlier. That is why we write left min equals to or less than right min heap. If this falsifies, then we will take the right heap value and we add it to the total cost and increment the higher count, and we repeat the loop until we have hired exactly k workers. So I hope you understood this explanation how we're gonna simulate this. Okay. So let's move to the next slide. So what we figured out? We figured out that using two minute help us to always choose the lowest worker from the valid ends. Okay. And the left and right pointers make sure that no worker is considered more than once. And also we don't have to pop anything from the array because that is not practically possible to do that because it will make our task much more tougher to do. Now this setup closely follows the problem's hiring rules and guarantees valid selections in each session, right? So I hope you understood the explanation of indentation. Now let's move to the next slide. Now, since we got the intuition of the problem, let's look into the approach how we're going to solve it. Our step one is initialize the pointers and heaps. We start with the two pointers, left and right, which basically starts from the this index left pointer and the right pointer starts from the last part of the array. Now we create two min heaps, left min heap and right min heap, and this will be created as a list because in Python we make it as a list and then we convert it to a heap. Okay. Now we fill the initial candidates. We fill the left heap with up to k candidates workers from the left, and we fill the right heap up to k candidates from the right, avoiding the overlap. Why we do this? Because it sets up our initial pools to pick from each hiring session. So this thing basically happens under while loop, while hires is less than k, okay, until unless you have not hired every candidate required. And here will be the while loop under it again. This will check for the left is less than or equals to the candidates and left is less than or equals to the right pointer basically, okay. And we pop the value and we push the values in the min heap here, min heap left, okay. And similarly for the right also we do it while the right is greater than or equals to the candidates and right is greater than or equals to the left. Yeah, makes sense. And here min heap right, all the values will be pushed in the min heap right and here min heap left, okay. Now after doing this, we hire workers in k sessions, right? We repeat the process until hires becomes k, like the while loop which I showed you earlier. Now we compare the top values from both the heaps. Okay. Now this is the heap. What we do? We do heap pop. Okay. Basically, we use the heap pop method of heap q. Okay. Heap q dot heap pop. Then we write the heap name here. Okay. So we pop the values this way from both of the heaps, left and right. Then we compare both of them, like which is smaller, right? In the left variable, like if I have written here, add the chosen cost to the cost. Otherwise, pop from right heap and hire from the end. And if left heap has the smaller or equal cost, pop from it and hire that worker. Right? This basically happens like in left variable, I will store the value of the left popped value from the min heap, and then I will check that if it is less than or equals to the right value. So if it is true, then total cost I will add that particular thing here. Okay. Otherwise, in the else case, what I will do, total cost, I will add this right here. Okay. So this way we're gonna do and add the values thereafter, and after that we'll increment the higher plus plus. Okay. Now at this step 4, we return the result after exactly k hiring sessions. We return the total cost. This is the total minimum cost to hire exactly k workers by always picking the valid lowest cost option. So basically, in summary, while hires is less than k, and while loop for the left, and while loop for the right, and then the left value, then the right value. Okay, then there is a comparison between them, left and right. Okay, and the total will have this if it's true. Otherwise, in the else case, the total will have the right. Okay, this is all happening within this particular while loop. Okay, and after that we will increase higher value because we have had one of the candidates, and after that we will just return the total cost. That's all. So I hope you understood the approach explanation. It was pretty easy and straightforward. So let's move to the next slide. The code is the exact copy of the approach discussed. Let's understand it line by line. So this is the code. Okay, so here we have taken the length, of course, of the cost array. We have started the left pointer from 0 and right pointer from last index to list for left and right heap, total cost and highest. Okay, now the code goes like this. Why highest is less than k makes sense until and unless we have not had all the employees. This is the first part of the left hand side. If you remember, I said that if the length of the left heap, okay, if it is less than the candidates. Why I have written this way? Because this will make much more sense to you. This is the heap, and this is the right heap. This is the left heap, and this is the right heap. Okay. Now, the what should be the height of the heap, length of the heap? It should be equal to the number of candidates, right? Suppose if there are three candidates, the candidate value is three. Therefore, we will be taking first three values and the last three values, and those three values should be in the heap. Make sense? So, if that is less than the candidate given, therefore it means that we have popped something from this particular heap and have moved it. Okay. So that is what we are doing, and that moving should be from left is less than or equals to the right pointer. They can overlap, but they cannot cross each other. We'll push it using the heapq function and heap push method this way, and we'll increase the left pointer. Similarly, the right also goes this way. If there is some pop was done from the right hand side and left has its complete value, then we will go. We'll try to push something here and from the back side. Okay. Now, after doing that, here in the left min, we will try to pop the first value if it exists. Okay. As I explained earlier, there might be a case that the left heap or the right min heap might be empty. So in that case, you have to put some max infinity there, right? So this is what we have put here. And if you can see it properly, heap of 0, why? Because always a 0 index in the heap will be the minimum value. This is the property of the heap in Python. This is how it works. Okay. And if it is empty, okay, left main, if it is empty, what we'll do, we'll put infinity in that case. Similarly, with the right also goes the same way. Now we have both the values or minimum values here. Okay. Then we will compare. If left is smaller or equal, we will take that and add it to the total cost. Otherwise, we will take the right side and add it to the total cost. And then we will increase the hires, the variable, because we have taken one of the employees in our consideration. Okay. And after this particular loop is completed, we return the total cost. Now, the time complexity comes out to be k log candidates. Why k log candidates? Because this k comes from this while loop. Because if you could see, we are just going up to the value of k. Okay. Now here, k could be, as given in the constraint, it was given from 1 to equals to cost length. Okay. So this k could be n also or 1 also, from constant to n. That's why, to make it much more understandable and much more clear, I have written k here because we are going up for up to k hires. Okay. And candidates. This candidate comes from the heaps which we are using, the left heap and the right heap. Because if you can remember, the heap carries only the candidates, the value of the candidates. If candidate is 3, it will carry 3. If it is 4, it will carry 4, right? So that is why, and any operation which is done in the heap, it takes log n time. And here the n is candidate. Fine. So that is why the total complexity comes out to be k log n, which is basically k for this and log k for this particular while loops. Fine. The space complexity is O of candidates, reason being we are using left heap and right heap. These are list basically, right? So this will store maximum of candidates value size, and it will be basically left heap plus right heap. It will be two of candidates, which basically boils down to a candidate only, right? Basically, it becomes 2 of n, 2n, which basically boils down to n only, right? Therefore, the time complexity or the space complexity is O of candidates. So I hope you understood the code explanation and the time and space complexity along with it. So let's move to the next slide. Now, since we have the understanding of the code, let's look at the dry run of the example. So I've brought down the code here already, so it makes us easier to relate it to the code. Fine. So this is the array given to us. Fine. I will just create two heaps. It will be left and right. I should also recreate this array. Okay. So now let's start with the dry run. So n is what? N is here 9. I've written here itself. And left pointer, let it be L, let it be R. Okay. Done. Left heap and right heap I have already drawn here. Now total cost. Okay. I will update the total cost here itself. Okay. And hires. Or let me write it here. Total and hire. Okay. Now while higher is less than equals to k. Right now higher value is 0 and k value is 3. Okay. So while length of the left heap is less than candidates, length of the left heap is 0 right now, if you could see. And candidate value is 4. And left is standing and it is less than equals to the right pointer. So what we will do, I will just skip it and we'll directly go and put this particular 3 values into the heap, 4 values into the heap. So basically L will come from, let me write the index values also, from here to this particular part, and they put the value serially to 10, 12 and 17. So this particular while loop gives this particular thing. Okay, now L is standing here. Again, the right, it is less than, the right heap length is less than the candidate. Yeah, true. Right pointer is greater than the left pointer. Yeah, because it is standing at the end. So I will just skip this part and bring the right pointer back into the fifth index, and we'll put all these values back into the heap in a organized manner. Like it will be 2, then it will be 11, it will be 2, then 8, 11, then 20. So this will be our main heap, left and right, and this is our indexing right now. Now in the left mean, we will take the topmost value from here. I guess it is 2 from both ends. Here also 2, and right mean heap also it is 2. Fine. If you do the left heap is 0. Okay. Now if we see left heap, left mean and right mean, they are equal, right? So I will add these two into our total cost, and we'll increase the higher value to 1. Then we'll go back, and along with it we're popping also, right? So we will pop it from here. Then we'll come back again. Fine. Now if you could see the first while loop, the length of the mean heap is less than the candidates, right? It is, because it is 3 and it should be 4. So what happens? And left pointer is also less than the right pointer. So what will do? The left pointer will increase and it will come to index number 4. And we will push this value into our left heap. Okay, fine. And right heap, the length of the right heap is exactly 4, so we won't do anything here. Okay. Then we will come again in the left mean heap, we will have 7. And the right mean, we will have what? We will have 2. Okay, from here. Now we could see that left mean is neither small or equal to the right. Right? Therefore, right has the minimum value. Therefore, we will add 2 here in the total and it will become 4. And we will pop it from the right heap also. Okay. And we will increase the hires to 2. Those 2 values we have taken. Now we will go back again. We will check the length of the left heap. It is 4 already, so this will be skipped. And then you come to the second while loop. The right heap size is less than candidate here because it is 3. And also the right pointer is greater than the left pointer, right? Because it is standing in index 5. So what we're gonna do? We're gonna move the right pointer and bring it here, and we'll push the value which is here, which is 7, right? That's all. Okay. Now we'll take the values pop the values from both the heaps. Both are 7. Now, since both are equal, we will come to this particular condition. We will add it to the queue. 4 plus 7 gives me 11, right? And this will be popped from the left heap. And we will increase the highest to 3. Okay. Now, when we go back, highest is 3, right? Is it equal? Is it less than k? K value is 3. It is not, right? So we will come out from this loop and we will return the total cost, which is 11, and which is equal to our output. So I hope you understood the dry run. So if you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, the approach, the code, and also if you don't know the concept of mean heap and max heap. And after that, do a dry run by yourself on 2, 3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. So let's move to the next slide. Now, since you're familiar with the problem and the solution, let's move to the lead code and code the solution. We'll start by initializing the length of the cost. After that, left PTR, it starts from 0. Right PTR starts from n minus 1. When we have left heap, right heap, then the total cost and the highest. While highest is less than k, while length of the left heap is less than the candidates, and the left PTR is less than or equals to the right PTR. What I will do, heap q dot heap push. The left heap will push the costs left PTR value. Okay, and I will increase the left PTR by 1. So now the same thing I will be doing for the right hand side. So this will get changed to right heap. Okay, and this will be reversed. While it is greater, right is greater than that, and this will also be changed to right PTR, and this one also will be changed to right PTR. Okay. After that, we'll go and have left minimum value, which will be basically left heap value if left heap exists. Okay. Else it should be float infinity. Okay. This will be changed to right heap. Same for this, and this will become right min. Okay. After that, we will compare if left min is less than equals to the right min, and if it is true, total cost total cost will be left min, correct? And it won't be left min directly, it will be basically heap q dot pop uh, heap pop from left heap. Okay, it will basically pop the minimum value directly. Else total cost will be heap q dot heap pop right heap. Makes sense? Then after that, we will increment the count of hires by 1, and I will return the total cost. Let's try submitting for the sample test cases. Okay, spelling mistake is here. Let's try again. Okay, the spelling of the PTR is wrong here. Now let's try again. Let me check. Okay, what's the mistake here? Saying left heap. Again, it's a spelling mistake. Here also it should be right heap, and let's try submitting again now. Okay, so mistake was basically here was that should not be +1, it should be -1. So we got wrong answer here. Let me check. So the mistake was basically in this particular case, I have written less than or equal to, but should be greater than or equal to. So let's try submitting again. Let's finally submit for the all test cases. So we have successfully submitted our solution. And the code of the problem is available in my GitHub repository. You can find the link in the description. Thank you, everyone.